In this video, we're going to look at the characteristics of electrochemical cells. This would be the higher level portion of the oxidation reduction unit for IB chemistry. So when we're talking about standard electrode potential, that's when if you have two half cells connected, the electrons will flow from the half cell that has the most negative standard electrode potential. And that's measured. We figure out what those are using connecting each half cell to a standard hydrogen electrode or an SHE. The standard hydrogen electrode has a potential of 0.00 volts. The other potentials are determined relative to it. So sometimes they'll have a negative reading and sometimes they'll have a positive reading, depending on their ability to oxidize or reduce. So there has to be certain conditions to have a standard hydrogen electrode. So you have to have hydrogen gas at 100 kilopascals and 298 Kelvin. You need an acid that has a concentration of hydrogen ions of 1.0 moles per liter. And you have a platinum electrode. Remember, platinum is not a reactive metal, so it's not going to be involved in the reaction. So you can take a look here. We have our hydrogen gas feeding into the electrode. We have our platinum electrode. We have a porous tube where the bubbles of hydrogen gas can escape because the hydrogen gas is being made here. This is actually sealed in, but because that tube is porous, the hydrogen can go through here and then leave out there. So depending on the half cell that the standard hydrogen electrode is connected to, it can either undergo one of two reactions. So it can undergo reduction, so the hydrogen ions would gain 2 electrons to become hydrogen gas, or the hydrogen gas that's in the electrode can be oxidized to make hydrogen ions and 2 electrons. So the way you determine that, we don't have standard hydrogen electrodes. Instead, we will look at section 24 of the data booklet to look at the electrochemical series. So if the E has a positive value, the half cell is reduced when it's connected to the standard hydrogen electrode, and the electrons will flow from the electrode to the half cell. If the E has a negative value, the half cell is oxidized when connected to the standard hydrogen electrode, and the electrons will flow from the half cell to the standard hydrogen electrode. So this is just a small portion of the data table in section 24 of the IB data booklet. So here are some examples. So the oxidized species would be the lithium ion and an electron. The reduced species would be lithium solid. So the voltage is negative 3.04. Potassium, same thing. This is the oxidized, this is the reduced, negative 2.93. Calcium, negative 2.87, and so on. And then there's our hydrogen. You can see that it's 0. So it's going to be the thing that we compare to. And then we have our copper and then silver are both positive values. So we can calculate the cell potential in the following. So you have your potential of the cell is equal to the electrical potential of the half cell where the reduction is occurring minus the half cell where the oxidation is occurring. So oxidation happens when the electropotential is less than 0. Reduction happens when the electropotential is greater than 0, but you don't change the sign in the equation. So we're going to work through an example. So in this example, we have a zinc half cell being connected to the standard hydrogen electrode. So we see that they're at their correct conditions. So the hydrogen gas is at 298 Kelvin and 100 kilopascal. This one's acting as the cathode. This one's acting as the anode. We have a 1 mole per liter hydrogen solution. and we have a zinc sulfate solution and our zinc electrode. So the oxidation is happening on this one and the reduction is happening on this one. So we need to go and look at the values on our data table. So if we look here, we can see that the hydrogen is 0.00, and then the zinc is negative 0.76 volts. So we're going to use those values. So our cell potential, we'll write that equation, is equal to the cell potential of what's being reduced minus the cell potential of the thing that's being oxidized. So the thing that was being reduced is the standard hydrogen electrode, so 0.00 minus, and the voltage for the zinc is negative 0.76. So we don't change the sign, so this actually becomes an addition. So our standard electrode potential is, for the cell, is 0.76 volts. So these types of problems are fairly easy to do. You just need to make sure that you look and find out which one's being reduced and which one's being oxidized. But the one that's being oxidized is the one that has the negative value, or the more negative value. So that's how you would solve those. So we can also take a look at electrode potential and the spontaneity of a reaction. So when the electrode potential is positive, this means that the Gibbs free energy value is negative. And remember, a negative Gibbs free energy value means the reaction is spontaneous. When the electrode potential is negative, the delta G is positive, so then the reaction is non-spontaneous. When the electrode potential is 0 and delta G is 0, the reaction is at equilibrium. So now we'll work through a practice problem. So in this scenario, this is taken from our Cognitive textbook. In this scenario, it says, rusting occurs when iron is exposed to oxygen and water. The following half reactions occur. So Fe2 plus 2 electrons makes iron, and the electrode potential is negative 0.44 volts. And then the oxygen, half an oxygen plus water plus 2 electrons makes 2 hydroxide ions, and the electrode potential is plus 40 volts. So we're being asked to calculate the cell potential and determine the spontaneity of the reaction. So remember, in the reaction, the half equation with the more negative electrode potential will undergo oxidation, and the half reaction with the more positive electrode value will undergo reduction. So we'll use the same equation we did before. So the standard electrode potential of the cell is equal to the electrode potential of the reduction, which would be the one involving the oxygen, minus the electrode potential for the oxidation, which would be the one involving iron. And then we look our values up. So we had positive 0.40 volts for the reduction reaction, minus, and then it was negative 0.44 volts for the oxidation. So that is equal to 0.84 volts. So this is a positive sign, so that tells us that the reaction is spontaneous. So we have a spontaneous reaction with this reaction. So electrolysis uses electric current to break a compound into its individual elements. So we've already learned that briefly in an earlier lesson. This reaction is non-spontaneous, so it's not, unlike the last one, it's not spontaneous. It can only occur when you apply an outside electrical current. So we have to drive the reaction with an outside energy source. And this happens, remember, either in molten ionic compounds or in aqueous solution. So those are the two scenarios where electrolysis is possible. Now, there is a problem with water. In aqueous solution electrolysis, water can actually be oxidized or reduced instead of the preferred materials. So it can be oxidized at the anode or it can be reduced at the cathode. So if it's being oxidized at the anode, the water becomes oxygen and 4 hydrogen ions and loses its 4 electrons. At the cathode, it absorbs 2 electrons to become hydrogen gas and 2 hydroxide ions. So there's 2 possibilities instead of the products that you're preferring to decompose. So the first example we're going to take a look at is the electrolysis of sodium chloride. So at the anode, if you have low concentrations of sodium chloride, it'll be water that's being oxidized at the anode. So that's not what you want. You want to oxidize the sodium chloride. So you need to have high concentrations of sodium chloride. And in that case, the chloride will be oxidized and you'll end up with your desired product. So we have the chloride ion becoming chlorine gas and 2 electrons. So it absorbs electrons from the cathode. So at the cathode, there's 2 reactions possible again. So this sodium can undergo reduction to become sodium metal, and its electrode potential is this. Or the water can be reduced to become hydrogen gas and the 2 hydroxide ions, and the electrode potential would be negative 0.83 volts. Because water is a stronger oxidizing agent, it's the one that's going to undergo the reaction at the cathode. So we'll end up making hydrogen gas and sodium hydroxide. And then the hydroxide ions can then combine with the sodium ions to make sodium hydroxide. So this is actually how sodium hydroxide can be made industrially. So through the electrolysis of sodium chloride. So we'll produce chlorine gas at one of the electrodes at the anode, and we'll produce hydrogen gas and then hydroxide ions that will form with the sodium ions that are left from the other reaction, and those will combine to make sodium hydroxide. So this would be a use for this type of electrolysis. We can also perform the electrolysis of water. So we can break water into its 2 elemental parts. But water in its pure state is a very poor conductor of electricity. So we have to add sulfuric acid to it to make a very dilute solution of acid. So you don't want to add too much. And then the electrolysis will actually create 1 volume of oxygen at the anode and 2 volumes of hydrogen at the cathode, because there is a 2-to-1 ratio. So you can see here, we've got the 2 water molecules becoming an oxygen. There's 4 hydrogen ions and 4 electrons. And at the cathode, it's undergoing reduction. So those 4 water molecules will take on the 4 electrons and become hydrogen gas and 4 hydroxide. So we end up with 2 parts hydrogen and 1 part oxygen. And this is what it would look like. So you could then, with these stoppers here, you could then release and collect the oxygen and the hydrogen to demonstrate that they have been separated. You could do a glowing splint test to demonstrate that this is oxygen, and then a burning splint test to demonstrate that that's hydrogen. We can actually also perform electrolysis of copper to sulfate. And in this example, you would end up with pure copper being formed at the cathode. So at the anode this time, water is being oxidized. So the 2 waters produce oxygen gas, and then the 4 protons and 4 electrons. So the water will be favored to be oxidized instead of the sulfate. And then the copper 2+ ions are going to absorb 2 electrons to become solid copper. So there you can see that the cathode is being plated with pure copper. So if you wanted to do copper plating, that's how you would do it. And that leads us to the concept of electroplating. So in electroplating, you're coating a metal with a thin layer of another metal. So an example of this is silver plating. The cathode undergoes reduction. So silver ions take on an electron to become solid silver. But you'll notice that the anode is also silver. So silver is undergoing oxidation over here to become silver ions and electrons. So the requirements for electroplating is that your cathode is the thing that needs to get electroplated, because that's where the solid metal will form. And then the anode has to be made of the same metal that needs to be plated onto the other metal. And the solution has to have the ions of the metal that need to be plated as well. So you would need, in this example, you would need a silver anode. Your cathode is the metal item you want to plate, and then the solution would need to be silver nitrate solution. So silver ions in solution. Now, when you're electroplating, the amount of metal that's plated onto the substance is dependent on 3 things. The time the current is applied, so how long you run the electroplating process for, the amount of current that you're applying to the cell, and then finally the charge that's on the metal ion. So we can actually use a formula to take a look at that. So Q is the charge in coulombs, I is the current in amps. You will remember that from grade 9 when we studied electricity. And then T is the time in seconds. So what that means is if the current doubles, the charge doubles too. If the time doubles, the charge doubles too. But if both the time and the current double, the charge will quadruple. So if we connected cells in series and passed the same charge through the series, the amount of products released at the electrodes would depend on the charge on the metal ions in each of the cells. So here's an example of how that's demonstrated. So we have 3 solutions and 3 electrolytic cells being connected in series, as we can see in this picture in figure 1, and the same amount of current for the same amount of time has passed through each cell. So we need to determine the ratio of the products discharged at the cathode of each of the cells. So we have silver nitrate in the first one, copper 2 sulfate in the third one, and chromium chloride in the third one. So the first thing we have to do is figure out what the half equations that will take place at the cathodes of each of the cells are. So remember, the cathodes are the ones that are undergoing reduction. So cell number 1, oops, I need to change it to my pen. Cell number 1, we have silver ions absorbing an electron to become silver solid. Cell number 2, we have copper 2+ ions taking on 2 electrons to make copper solid. Cell number 3, the chromium 3+ needs 3 electrons to become chromium solid. So the ratios would be the following. So you would have 1 mole of silver, half a mole of copper, to 1/3 of a mole of chromium. It's because you need 3 times the number of electrons to reduce the chromium. So if we only have 1 electron on the first one, you need 2 for the next one, so you'd only get half the number of moles of copper 2+, and you would only get 1/3 of the number of moles of chromium. So here's a second example from Cognity. So this one says 1 mole of copper is deposited at the cathode of an electrolytic cell that contains aqueous copper 2 sulfate. What amount in moles of silver would be deposited at the cathode in the electrolysis of aqueous silver nitrate if twice the amount of current was supplied for twice the duration? So the first thing we need to do is figure out the half equations. So we have Cu2 plus 2 electrons makes copper solid. And we have Ag aqueous plus 1 electron makes silver solid. So to produce 1 mole of silver, you need half as much charge as 1 mole of copper. So 1 mole of copper automatically would cause 2 moles of silver, but because we doubled the charge, we times that again, so then it would be 4 times, because we've done that for twice the duration. So we'd end up with actually 8 moles of silver being produced. So if we had the same amount of charge and duration, you would get 2 moles of silver. But because we doubled the charge, we'd get 4 moles, but we also did it for twice the length of time, so we get 8 moles. So the answer is 8 moles.